Welcome everyone to our lecture. So in this lecture, we'll be looking at something called secular motion. All right, so I'll just explain that now. All right, so we'll just look at two types. We'll look at something called uniform secular motion. We'll look at something that is called non-uniform secular motion. So previously what we've been doing is we've been looking at cases whereby you have something that is moving in the x direction after some time it's here. Sometimes you'll throw things up so it will move from here and then go up to here, and then this will be y. All right. Then sometimes you just have something that moves like in an incline, for instance, it moves this way, and then this will be delta s. All right. So all of this was basically translational motion, or linear, if you may like to actually say. Now, circular motion is a situation whereby I have someone or an object and it's just moving in a circular path. So we'll be looking at the mechanics and everything of that. Of course, the following chapter that I'm also going to introduce is a situation whereby something is rotating. The difference, for instance, when an object is moving in a circular path, it's just that object following a circular path. This is similar to you running when you're running a circular field, for instance, in a circular field. You are just running, you are not rotating, you are running, you are straight, you are just running, right? But then if you're rotating, I mean, you could be rotating, maybe this is you, and you could be running this way, but maybe you could also be rotating that way. So you are running like that. I mean, a good example of this is maybe a yo-yo. Okay. So I'll get into that when I actually talk about rotation. So at the moment, what we're focusing on is just circular motion. All right. I'll describe everything when we get to rotation. Now, since we're talking about circular motion, so we're talking about circles. So it's best that we actually talk about properties of a circle. So I'll start in a way from the basics so that you just understand how a circle is basically set up mathematically. So a circle basically is if I draw a point and I draw equal distances from that point in different direction, and these lines are equal. If I draw equal lines and then these lines are just equal, all right, from the center they are equal. If I join where those lines end, basically I get a circular path. So if I drew them up to scale, of course it would be a perfect circle. So these lines are called radius, and then we just denote them as r. Okay, so that's a radius. It's just basically the distance from the center to the path, or to the circular path. Basically, that's basically what the radius is. All right, you can actually find for instance, if a person is here and then this person starts going in a circular path like this, they go all the way around, and then they started where they started, they come all the way around and they stop here. I can find the distance that is covered. This distance is called the circumference, which is the total distance. So that distance is just given by 2 pi r. Now pi is just a number, it's a special number in mathematics. It's a very fascinating number. There's two numbers, it's just pi, and then there's another one called e. You'll learn about these ones as well. Normally when you get to varsity, you also learn about this e number. All right, but okay, for now, I mean, just know that these numbers are special. Basically, you deal with them a lot in nature. All right, so we can find this distance, and this distance is called the circumference. All right, so that's basically the circumference. Should be an m here. All right, so that's just basically the circumference. Okay, so that's basically that distance. So also, if I have a circle, let me say someone is like undergoing a circular path, and then there's my radius r. I can find the area of this radius, and the area of this radius is just given by pi r squared, basically. All right. So that's one thing that you should also know about a circle. And then what else should you know about a circle? If someone is somewhere and then they're about to undergo a circular path, so let me just draw a circle like that. There's a circle, then there's the center, and then there's r here. So they started here. All right, so if they, for instance, cover this distance, let me use a different color. If they cover this distance here, all right, so this distance, let me just say they stop somewhere here, we can actually find certain things about that distance. This distance is r, this distance is r. There's something that we call an angle, and then that angle is called theta. In reality, theta is just given by this side, so this path here is actually known as the arc. All right, so this one is known as the arc. All right, so that's the path. So this arc can actually go around, which basically makes one revolution. All right, so theta is going to be given by S, which is the arc, over R. Basically, that's the definition of theta. It's just a ratio. That's basically what theta is. So I'll come back to this theta in the next chapter when I'm actually discussing rotation. But for now, we should know that, okay, we measure this theta in degrees. For now, we'll just measure it in degrees. All right. So like 0 degrees, 30 degrees, 40 degrees. So the larger your degrees, basically, the more distance you covered, basically. So if, for instance, 30 degrees is a little bit smaller, there's 30 degrees, there's your arc. So your arc is a little bit smaller if it's 30 degrees. If it's 60 degrees, then your arc is a little bit bigger. Now your arc is bigger, and then this is 60 degrees. Then if it's 90 degrees, your arc is even bigger, right? There's your arc, and then it's 90 degrees. So you can see that theta is changing. If it's 180, then your arc is actually becoming more bigger and bigger. And then basically this is your arc, this solid line is your arc, and then there's your theta is 180 degrees. All right, so you could go all the way around. I'm not sure if you could see now because I cut my screen somewhere. So you could actually go all the way around, and then basically, and then have a theta, which is going to go around like that. So if I started somewhere here, theta is going to go around that. So now we introduce something. If I move from this point, and I go around and come back to that point. So basically I start at that point, and then I go like this. I go like this, I go like this. So basically I'm covering the whole path. All right. So we already know that I've basically covered 2 pi r in terms of my distance because it's the whole path. So that whole path moving from this point back to that point is called a revolution. So basically I have made one revolution. So that's very important. That's called a revolution. So normally I'll just basically abbreviate this as rev. So meaning that is revolutions basically. All right. So one revolution, basically one rev, is going to be equals to 360 degrees. So when you cover an angle of 360 degrees like this, you come back here. Basically, if this is 360 degrees, it's because you have made one revolution. Basically, that's what it means. All right, so that's basically what a revolution is. Okay, all right. Okay, so this one of course is a semicircle. This one because it's half, right? So normally it's known as the semicircle, meaning that it's half the circle. Basically, that's what it means. All right, and then so I've covered everything. So there are special properties that are associated with these revolutions. All right, now in another chapter called oscillations, I'm going to come back to this. So this chapters, circular motion, rotation, and oscillations, they are going to be linked, and waves, they are going to be linked basically. So I'll keep referring to these chapters. So you shouldn't lose knowledge on these chapters because I will be building up on these chapters. All right. So for instance, if I start here, okay, some people may agree that I may actually cover a certain distance over a certain period of time. All right. Now there is a possibility that I may go around. If I'm very fast, I may go around in 1 second. Sometimes in 1 second, you may find out that I went around twice. Sometimes in 1 second, you may find that I went around 3 times, depending on how fast I am. Sometimes you can even go 400 times in 1 second. So basically that thing that I'm talking about, how many times did you go around in 1 second, is actually called frequency. So I'm going to call it F. So this is the number of revolutions. How many revolutions did you make? Meaning that how many times did you go around, okay, in a circular path in 1 second. So this is the most important thing, in 1 second. So the units of this basically is known as hertz, which is a person, or you could just say per second. This is fine. These are just units. That is frequency. Okay, something that is linked with frequency is something that is called a period. Let me just say, for instance, it takes me some time t to just complete one revolution. Okay, so the period then is defined by the time that it took me, whatever the time is that it took me to cover one revolution. That's basically what a period is. How long did it take me to move from point A back to point A in a circular path? How long did it take me? That is the period. Okay, so the period is measured in seconds. Okay, so this is the frequency. Again, we'll come back into these things. This is the frequency, and then this is the period. Period. All right. And we can relate this. For instance, the period is related to the frequency by 1 over f. Basically, we can actually relate this. All right. So we're just talking about properties of a circle at the moment. We haven't done much of physics. We're just doing, now we have started doing physics because we're now talking about periods and frequencies, and then we're going to use this a lot. I mean, we use this every day in our lives, basically. As I'm talking to you now, I'm basically producing sound waves, and sound waves have a frequency and a period. So this is just so fundamental in physics. It's almost everywhere and everything. All right. But don't worry, we'll get into that as well. Then I'll just explain everything when we get there. All right. All right. So I could also, if you look at this, let me say, for instance, I cover one revolution. So if I cover one revolution, it means that the distance that I've covered is 2 pi r because I've went around. So I would have went around. I mean, I would have said moving from point A back to point A. And then if this is r, and then the distance that I would cover in that one revolution is 2 pi r. Also, I know that for this one revolution, the time that I take is actually called a period. And I know that the speed is given by distance divided by time. But then the distance is going to be 2 pi r, but then the time for one revolution is going to be the period. Okay, so basically now I have an equation that says to me that in actual fact, if I know the period, I can actually find out if this person is moving at a constant speed, of course, then I can actually find out how fast is that person traveling. You can't necessarily use this equation. If you can get it, it's just going to give an average if you use this equation. But then if the speed of the person is changing, it won't give you their speed at every moment in time. If their speed is constant, then whatever speed you calculate here is going to be that speed at each and every point in time, because the average speed is going to be the same as the instantaneous speed. Again, I have linked the chapters that you should be familiar with where I've discussed these concepts. But if the speed is changing, which means that the person is accelerating, then you can't actually just say the speed is going to be given by this equation everywhere. This just becomes the average velocity. It just becomes the average velocity for one revolution. All right. So if they don't cover one revolution, you may have to actually find out how much distance did they cover, and then take that distance. How long did they take to cover that distance, and then take that period. Then you find the average speed. So you have to be very careful. All right. So as much as this is like a basic definition of how we can find speed, is not an end all be all type of an equation for this. All right. So it just depends on the scenarios. So this is true for one revolution, constant speed, definitely everything is fine if that's the case. But then once your speed is changing, you're covering more distance, then you have to tweak it a bit. All right. Okay. So another thing, maybe one last thing that I have to discuss in terms of circles is that if I have a circle, there's my circle. Then I have a radius r, there's my radius r, right? From the center to there. I could draw a line such that that line is perpendicular to r. Any line that I draw that is perpendicular to r is going to pass here, something like that. This line is actually known as a tangent. That's what a tangent basically is. It's just a line that is normal to r, meaning that it's perpendicular to r. That's basically what it means by a tangent. All right. So that's a tangent. This is going to be very important, and then as you'll see now. Okay. So let's just look at an example. So for instance, an EG, let me say, for instance, I have a circle and my circle has a radius of 5 centimeters. All right, so just change this 5 centimeters immediately to meters. Just make it meters. Just going to be 0.05, I believe, because you're just going to divide that by 100 basically. So it should be that, or you could say it's just going to be 5 times 10 to the power minus 2 meters. Either way, it should be the same. All right, and then I'm just going to say, then the object that is moving in this circle is actually moving at 3.8 minutes per revolution. Basically, that's how much they cover. Now, I don't know what is that. So the question is, I need to find the frequency, and then I need to find the period, then I need to find the distance that will be covered by this person, assuming they're moving at a constant speed. Then I'm also going to find the velocity. Now let's look at the frequency. All right. But then given this, I mean, if you call this, let's call it what? Let's call it P, whatever this variable P is. But if I look at this P this is the same as delta time per revolution. So already I've told you that, hey, I mean, minutes is time, and then revolution is just how many times you went around. And remember, I defined the period as how long, however time per rev. So basically, they have given us period. It's just that we have to change it to seconds per rev. So I can do that. I can say, well, then my period t, I'm going to find the period first, is going to be equals to minutes per revolution. All right. Then what I would say is just change these seconds and then just make it cancel the minutes. So 1 minute is just going to be 60 seconds. And then it's just going to cancel this. We did this. So basically, this is basically 3.8 multiplied by 60. And then the answer is going to be seconds. It's just going to be seconds. In principle, the period is seconds per revolution. But let's just put seconds. How long do you take to make one revolution? It's just interested in the time. So I'm not going to put the rev. Right? It's there, but I'm not going to put it. Okay, so basically this is going to be 2 to 8 seconds. So that's basically my period. Okay, this is how many seconds they will take in order for them to cover this this to go around in a circle. All right, so they are actually pretty fast. If I want to find the frequency for this, it's just going to be 1 over t, which is 1 over 228, which is going to be equals to this is going to be equals to 4.4 times 10 to the power minus 3 hertz. All right, so frequency is measured in hertz. All right, so let me just make space. All right, so how much distance did they cover? Okay, so since we know r, it's pretty easy for us to find the distance. The distance is just going to be given by 2 pi r, and that's just going to be 2 pi. Remember, pi is a number, and then put whatever r in meters, which is 5 times 10 to the power minus 2 in meters. That's basically it. All right, so they are basically going to cover 0.31 meters, which is approximately 310 not 310, which is approximately about 31 centimeters. All right, so that's basically the distance that they'll cover in this, that object will cover in that thing, in that circle, basically. All right, and then how fast were they moving? We are assuming that they were moving at a constant speed, so v is just going to be equals to the distance divided by time. All right, so if we just know the time for one revolution, and since they're moving constantly, it doesn't matter, the speed won't change. So their distance is going to be 0, sorry, this is going to be meters, not centimeters. I don't know why I did that. All right, so this is going to be 0.31 meters, and then the time is 2 to 8 seconds. Don't put the seconds. Then this is just going to be equals to, all right, so this is going to be equals to 36 times 10 to the power minus 3 meters per second. Basically, that's it. That's basically what's going to be. All right, so I think this is a decent example that just showing you how you can actually find different things using that. All right, so now let's get into some more important stuff. Let's get more where the physics now is going to come from. Okay, all right, so if I have a circular path, there's my circular path, blah 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 blah. All right, there's my circular path, and then there's my radius. So this is my radius point. Okay, if for instance I place an object here, this object, if I draw a line that is going to be perpendicular to that object, assuming that is going to be straight to the center, I can actually find out what the angular speed is going to be. There's going to be some angular speed. Let's just say this speed is v0. What happens when it's here? Let's say the speed, the magnitude is the same, but now they are here. So let's just call it v1, for instance, when they are here. When they are here, the tangential velocity is going to point in that direction. Just call it v2 if you want. When they are here, you could draw a tangential velocity. because you want them to move in a clockwise direction. Then this is v3. You could do this for anywhere basically. All right, this is going to be v4. All right, so these are tangential speed at each and every moment in time. All right, now the question is, well, we know, so we're saying that v0 is going to be the same as v1, it's going to be the same as v2, it's going to be the same as v3, it's going to be the same as v4, which means that this is constant basically. This is constant, is not changing. So the magnitude is constant, right? This is the magnitude is constant. Now the question is there any acceleration here? All right, because we all know, for instance, that if it's just a straight, if it's just like this, it's moving that way, it should be moving straight, but it's not moving straight. So we're trying to figure out why is it not moving straight. And then if it is moving in a circular path, is there something else that is actually making sure that this thing is moving in a circular path? Let's find out, is there going to be acceleration? We know that the acceleration is going to be delta v over delta t, for instance. That's fine, right? We know that. So which means that if there is a delta v, then there is definitely acceleration. All right. So let's just find between the two, v1 and v2. What is delta v? Well, delta v is going to be equals to v1 minus v2. These are v1 minus v0, sorry. These are vectors. Let's draw it. All right, so let's look at v1. v1 is going to go like that. There's v1. All right, so this minus v0. So I've already taught you vectors, so you should know how I'm adding this. I mean, this is the same as v1 plus minus v0. If you haven't watched the video on vectors, again, go to the description. It's going to be linked there. All right, so this is basically going to be minus v1 is going to be this vector here, which is minus v0, sorry, not v1. So you can see that my delta v vector is going to point like that. And remember that the acceleration is going to be in the same direction as the delta v vector. So which means that my acceleration vector is also going to be like that. That's my acceleration. So in this case, move from here to here, my acceleration vector is going to be in that direction, more or less, because I haven't drawn it. I didn't draw it. So this is the a vector. I mean, you could do this for any of them, really. You could do it for v4 to v0. So if you're moving from v4 to v0, you could do it. You could say, well, v0 is going to look like this. This is v0 because it's the final. And then you could say, well, v4 is basically going to look like that, but the minus of it is going to look like that. And you could see here that your delta v is going to look like that. So that is why moving from v4 to v0, your delta v is going to look like that. So it seems that wherever the direction is delta v, that's the direction of a. So a is going to look like this. So from this, you can see, I mean, if you do all these vectors, you draw them, you'll find that there's always going to be a that is going to be in that direction. There's always going to be a. But a is always going to point in this direction. Now, this is why, for instance, remember a is related to the force. So really, I've taught you forces. I've shown you that whenever there's acceleration, there's a force. You can link it. I've taught you energy. So I'm assuming that you have all of this knowledge, okay? So what basically happens is that when you are here, your object wants to go in this direction, but it feels the acceleration in that direction. So it can't go there, so it ends up somewhere here. When it's here, it wants to go in that direction, but then there's acceleration pushing it downwards and then can't go there, so it ends up somewhere here. Again, there's acceleration, it wants to go there, but it can't, it ends up somewhere here. It wants to go there, but so it wants to go there, there's acceleration there, it ends up somewhere here, and so forth. You can see that the acceleration is always pushing it towards the center. So you end up with an object that is now moving in a circular path. If there wasn't this acceleration, remember the acceleration is a push and a pull, right? You even remember in free fall when we were actually throwing something up in projectile motion. We were throwing something up and then the acceleration was facing downwards and then our object was slowing down because it was feeling pushed, and then it came back faster because now it was actually pushed in the same direction and came back. So the acceleration is always associated with a push or a pull, basically. Okay, so in this case, for instance, this is the acceleration is always forcing the object not to go in the direction of the tangential velocity. So this here, this speed here is known as the tangential velocity or speed. All right, the magnitude is velocity, but then the magnitude and direction is going to be velocity. The magnitude only is known as speed, and then the magnitude and direction is known as the velocity. All right, so this is actually what is keeping these objects in a circular motion. So it turns out we can call this acceleration the radial acceleration, or we can call it the centripetal acceleration if you want. You could say it's AC. It is going to be given by whatever the velocity is at that point, all right, squared divided by r. That's basically how you will find the magnitude of this radial or centripetal acceleration. So I'll just write it again. AR is going to be v squared over r. So if v is changing, you have to find it for each and every point. But if v is not changing, then it's the same throughout the magnitude, right? So this is known as the centripetal acceleration. So this is very important. You'll see with the examples that you'll be dealing with that you actually encounter this every day. All right, so you could say radial acceleration, you could say centripetal acceleration, but the common one that we use is centripetal acceleration. Okay, so this is the important part when it comes to this one. All right, so let's maybe try some simple example, very simple example, whereby you have a circle and then the circle, there's an HE, that's another example. So you just have a circle which basically has 3.5 meter radius, and then you are told that the object is moving at 8 meters per second. It's basically constant. You can find the radial acceleration, which is just v squared over r, and this is just going to be 8 squared over 3.5, and that is going to be 18.3 meters per second squared. All right, because this is acceleration, so it's going to be meters per second squared. Okay, so what do we know? We know that if there's acceleration, there must be a force, because we know that the sum of all the forces is always going to be equal to ma. We know this. All right, so which means that this here, ma here, we can actually say, well, the acceleration that is actually resultant for all the forces, because there are forces that are acting that are actually making it move in that direction, is going to be mar. So which means that this is going to be v squared r. So therefore, the sum of all the forces at each and every point, you'll see that is going to be equals to mv squared over r. Then the direction is always going to be pointing in the radial direction. So it's always going to be pointing in the radial direction. And then it's going to be different, of course. You can just say in the direction r if you want, okay? And then that direction r is basically the vector that is pointing in the radial direction, the direction towards the center of the of the circle itself. That's basically how we can actually do it. All right, so let's just look at a simple case, for instance, just so that I can demonstrate that. All right, let me say you have a horizontal circle, right? There's your radius, then there's your horizontal circle. So you're moving a stone. I mean, it could be a stone, it could be anything. You're moving it in a horizontal circle. So this is a similar case whereby you take a rope, you take whatever rope, and then you basically tie whatever object, and then you raise your hand, and then you start spinning so that to create a horizontal circle. If you do that, you will notice that there's going to be the force here, mg. Then since you have the rope, there's going to be tension force that this object is going to feel in that direction. And maybe let me just say you are basically rotating it in that direction. So with some speed v, let's just say you're having constant speed v, which is 15 meters per second. And basically maybe the radius, let's just say it's 4 meters. And then we want you to find the centripetal force. All right, so what is happening is that the centripetal force is always going to be equal to the force that is going to be facing in the direction of the object. So for instance, actually this one everywhere is actually going to have the same tension everywhere because it's a horizontal circle. So the only force that is making sure that is keeping this up, because this object wants to go there, but this tension is forcing it to go inside, which is this tension force. All right, so it can't go there, it ends up somewhere here. When it's here, it wants to go there, but the tension going this way, so it ends up somewhere here. When it's here, it wants to go this way, but then the tension is forcing it this way, so it ends up somewhere here. And you can see how it is. I mean, even when it's here, it wants to go that way, but the tension is forcing it that way, so it ends up somewhere here. All right, so actually I can't draw it very nicely when it's a horizontal circle, but it's a horizontal circle. So when you're looking at this, for instance, this is y, and then this is x. All right, this is y, this is x. I can choose this as positive, it's fine, because it's going to cancel. So the sum of all the forces is going to be equal to the centripetal force. Remember, the centripetal force, which is Fr, is just going to be mv squared, the magnitude given by mv squared over r. That's basically the centripetal force, all right, which is the force that is actually due to, that is actually as a result of these objects moving around. So you could find that this is just v squared over r. Okay, whatever the direction is, that's always going to be inside. So in this case, you can sum all the forces in the x, which is minus t. Then also your radial force is also going in that direction. All right, so your radial force is also going in that direction, so it's also going to be minus the direction in the x direction, and then mv squared over r. Now in the y, it doesn't play any role, because the only force mg doesn't actually affect the particular object moving in a circular motion. All right, so that force doesn't play any role there. Okay, all right. So in this case, for instance, you can find it. That's why I said it didn't matter, because the negatives are going to cancel each other out. So basically, you have mv squared over r. So you could actually find out what would be the tension if you wanted to, and the tension would be the same as the centripetal force in this case. All right, so you could find the tension if you want. You could say the tension is just going to be, let's just say this is the mass, 2 kg. So you could say this is just going to be 2 kg, and then this is 15, and then this is 4. 15 is squared. All right. All right, this is going to be 112.5 newtons, basically. All right. If you ask what is the centripetal force Fr, the centripetal force will be the same as the tension, which is the same as mv squared over r. Okay. So remember, what is actually making objects go around is basically that centripetal force. Remember, there's a centripetal acceleration, and the direction of the acceleration, remember, since F is equals to ma r, so whatever the direction of r is going to be the direction of the force. So here r is going this way, so which means that F is also going that way. Here r is going that way, which means a is going that way, which means that Fr is going that way. Here a is going that way, AR is going that way, which means that FR is going that way. Whatever the direction of the acceleration, that's the direction of FR. That's basically, it's always pointing towards the center. All right, so this is just me introducing concepts, sometimes with examples as well, so that you sort of get an idea as to how this thing actually is going to work. All right. All right, so another example that we can consider, just consider sort of a car, a cart, whatever. They use this in circuits. I don't know what to say, but let's just say you have something like that, and then I just want to draw it like this, and then it's moving a circular path. All right, and then there it is. All right, so there's my cart. It'll start somewhere here. So I want to move it such that at this point it must have some tangent velocity v. All right, I don't know that v. Maybe let's just say this is the mass of this. It's just basically, let's just say 100 kilogram. All right, so if it moves at a particular speed v, that there's a minimum speed v that it can move with, and that minimum speed v is actually going to ensure that it actually stays in a circular path, because if it stands still here, it's going to just fall. Why would it fall? Because here there's two forces. Since there's a surface, there's a normal force, and then there's also mg. So there are two forces here. So if it just stands still, it's just going to fall. But if it has enough, velocity, tangential velocity, it's actually not going to fall. It's going to actually go around like that. All right. So even when it's here, maybe somewhere here, it may be going this way when it's here. All right. So I want you to find So I know that there's going to be mg here. I want you to find the force, this Fn, that is going to be required such that it actually maintains the constant speed here. All right. So in order for us to do that, for instance, we need to find out what would be the minimum speed that would be required at the top, right? In order just for it to maintain the in order for it to maintain the circular, to move in a circular motion, we have to find the speed first. All right. So we could find the speed. We could say, well, Fn minus, this is minus minus, and then this is going to be mg. All right. But we also know that the radial acceleration is going to be in that direction. So Fr is going to be in that direction there. And Fr here is also going to be in this direction here. So Fr changes. So even Fr is minus in the y direction, and then mv squared over r. And this is very important. Remember, the sum of all your forces is going to be equals to whatever mar. So if there's acceleration, there is acceleration, and that acceleration is r. So that's why we're saying that the sum is going to be equals to that. All right. Now, in order for you just to find the minimum speed that is required there, so what you do is you set Fn to be equals to 0. Then you are going to get the minimum speed that will be required, that the car must have in order for it to maintain a circular path. And then if this is 0, then the negatives kill everything. And then you have mg is going to be equals to mv squared over r. So the m's are going to cancel, so I don't need the mass. Then I can find the speed, which is just going to be the square root of gr. So I can find that the minimum speed is going to be 9.8. Then the radius, so maybe this circular path, I could say maybe is going to be r is going to be equals to 5 meters. Then I could just say this is going to be 5 meters. All right, and then if I say that, I could find the minimum speed v, and that minimum speed v is going to be given by, so it must actually move at 7 meters per second. That's the minimum speed that it should actually move with. If it doesn't move with this speed, then we basically are in trouble. All right. So it must actually move with this speed in order for it to, in order for it to actually, in order for it to maintain the circular path. Now the question was, what would be the normal force that would be required in order to keep the speed constant? So here at the bottom, you can see that the forces that are acting as Fn is acting up, minus mg is acting down, then Fr is acting up. Okay, so what is Fn? That's the one that I'm looking for. This is going to be mg plus Fr. So this is going to be mg plus mv squared over r. So you'll need to apply this type of a force. The surface has to apply this type of a force in order to maintain the speed, to make sure that the speed is actually maintained here. All right, and then that force actually that would be is going to be m, and then you could just say g plus v squared over r if you want. Some people like doing that, and then this is 100. Turns out we do need the mass here. And then 9.8 plus we found the speed to be 7 squared, and then we found this to be 5. All right, and then your normal force that you will need in order to maintain that is going to be equals to, so this is going to be equals to 1960 Newton. All right, that's basically how much normal force you are going to require in order for you to actually get that car to be moving at that speed. All right. In most of the cases, this is not true. Well, you could make it. I mean, if you're controlling the engine, maybe you could control it such that you try and maintain a constant speed. But in most of the cases, the car has different acceleration. For instance, it would normally speed up this side. It would just speed up, speed up, speed up, and then slow down, slow down, slow down. And then if it still has enough velocity, it will come past and then speed up, speed up, speed up, and then it will just continue speeding up, slowing down, speeding up, slowing down. So the acceleration will be changing each and every moment. Okay, it just depends on the scenario. If you do apply force, you do maintain it, you do drive it, you could maintain the constant velocity, you could maintain a certain speed, or you could actually speed up. So for instance, maybe you leave it, you don't accelerate here because it's speeding up by itself, and then when you get here, you start switching on the engine, and then you actually accelerate so that you become faster and faster and faster. All right, so you could actually do that, and we're going to analyze that because now we are going to get to non-uniform motion. All right, so now let's look at a situation whereby the object is actually accelerating. So for instance, let me say I have an object. So let me say I have an object. There's my object. There's a tangential velocity v0. So this object is going to undergo uniform circular motion. So since it's undergoing, not uniform, sorry, since it's undergoing circular motion, we already know that it's going to have centripetal acceleration. So there is going to be centripetal acceleration. That one is a given because it's going under, because it is going, okay, I have to draw it somewhere here, because it is going circular motion. So that is why that we are saying that it's going to have circular centripetal acceleration by virtue of just going through that. Okay, so even here, for instance, when they are here, they have this tangential velocity v, and then of course there is this centripetal acceleration, and then again the centripetal acceleration, then the velocity is in that way. All right, so what you discover is that if they are accelerating, the velocities are not the same. So this will be v2, this will be v3. Right, so the reason why, so since the velocities are changing, it means that there's another type of acceleration that is actually causing this acceleration to change. Remember, the centripetal acceleration is only keeping the object in circular motion. That's the only thing that it's doing. It doesn't make the object speed up or slow down, it just keeps it in circular motion. So if the object is speeding up or slowing down, it means that there's an additional acceleration that is actually at play there. All right. So in this case, it means that there's acceleration. It turns out that the acceleration that is actually there is the acceleration in the direction of the tangential velocity. So I mean, this is a case whereby you're assuming that that acceleration is constant, and then you say, okay, fine. So if that acceleration is constant, I'll have a tangential acceleration, which is a10, and then it will be in the direction of the velocities, right? So you could have it such that the magnitude is constant, but then the direction, of course, as you can see, it can never be constant. So I'll start calling it AT from here. All right, so from now on, I'll just call it AT. So it means that there's two types of accelerations here. There's AR and then there's AT. So if your object is speeding up or your object is slowing down, it's because there's tangential acceleration. So if you look at this, since there is tangential acceleration, if you look at this vector, you have A10, there's your AT going like that. Then you have your AR, there's your AR going like that. Then you can see that the resultant acceleration is that. And then it has an angle theta here. Okay. So there is basically going to be acceleration vector A here, acceleration vector A here, acceleration vector A here, and then there's also acceleration vector A here. All right, then you can have theta in these directions. Okay, can have theta here, can have theta here, and you can have theta here. All right, so you can have like theta. Of course, these angles are different depending on where you are, generally speaking. All right. Okay, so that's basically what you're going to have, and different directions, of course, depending on whatever it is that you have. All right. Okay, so based on this, you can actually see that we can actually write quite a number of things. So what we can do is we can say, well, it means that the acceleration, the total acceleration, is going to be given by AR plus AT. And I can find the magnitude of that acceleration by simply taking AR squared plus AT squared. I can actually find the magnitude. You could also find the direction theta, but then you have to take whatever is on the y and to whatever is on the x. For instance, if you look at here, for instance, A10 is on the x and then AR is on the y. But for instance, if you look at here, AR is on the x and A10 is on the y. So it changes, right? So since it's changing, you can't just say it's going to be a tangent and divided by AR. You can't just do that, right? So then to find AR is simply, you remember, V squared over R. So it depends. So AR is changing because the speed is changing. So AR here, for instance, you use VO, AR here you use V1, AR here you'll use V2, AR here you just use V3. So you can see that AR is changing. So once your object starts speeding up, even your centripetal acceleration changes. Okay. Now your tangential acceleration is just given by changing v over changing time. So for instance, if you wanted the tangential acceleration between this point and this point, remember this is v0 and v1, you should simply say this is just like v1 minus v0 over whatever time it took to move from this. If I call it point A and I call it point B, whatever the time that it took to actually move that time. That's basically how you would actually find the tangential acceleration. Now, a good thing generally is just to assume that it is constant, because it's a little bit tricky if it's changing as well. So for instance, if I just apply a force on an object when it's somewhere, maybe when it's here, I apply a force and then I leave it, then what you notice is that the centripetal acceleration is going to change, because as it's going down, it's going to go faster. As it's going back, it's going to be slower. It may actually have enough speed to reach here, it may not. It just depends on the force that I gave it initially. All right, which is different, for instance, if I drive the motion, meaning that I don't actually stop applying force as I'm moving, and then I'm controlling how fast my object is going to go. In that way, I can actually maintain a constant tangential acceleration in that sense, because I'm applying a force, and then that force is actually a result as to why my speed is actually changing. The important thing here is that even if I'm driving this motion, the tangential force, the tangential, whatever the force that I'm applying, of course, is is in that direction. It doesn't necessarily mean that that is the force that I'm going to get. The tangential force is sort of a resultant. It's a resultant force that you get. So it's a component of a resultant force that you get, basically. All right. Okay, so let's look at a situation whereby I still have my constant tangential force, and then basically I just want to see how the forces are going to influence this motion. So since I actually have the tangential acceleration in that direction, remember, if I have acceleration, it means I have force, because force is ma. So if I have tangential acceleration, then I must have force, tangential force. If I have force, which is going to be equals to m AR, so which means that I can actually have the centripetal force. So whatever acceleration that I have, there's a force associated with it. So since A10 is in the direction of the tangential speed, then in this case it means that I am going to have the tangential force, and then I'm going to have the centripetal force facing that way, and then I'm going to have my object moving in a circular path like this. And then even here I am going to have F10, and then I'm going to have FR, and then here I'm going to have my FR, and then I'm going to have my F10, right? Whatever force that is tangent to the circle, and then that's always my FT, and then like that, and then this is my FR. So let's look at an example, for instance, where I have a cut. Maybe let me just make space. Let me see, let me make space this side. All right, so let me just look at a case whereby it's like I have a cut. There's my cut, similar to the example that I had up there. All right, and then my car is going to be somewhere here, and there's the car, and then it's going to go like that. Okay, so I think it's going to shine like that. All right, so you could have a car that is moving somewhere here. So basically there's a surface. I mean, there's circuits whereby something like this happens. Those guys do crazy stuff. All right, so you could actually have a car that is moving like that. Then let's just have it somewhere here as well. All right, so I just have this car moving in this way. So it starts here at the initial velocity. It's going to be v0, and then this one is going to be v1, and then this one is going to be v2, and then this one is going to be v3. All right, so there are different forces acting on this object, and the object is changing speed because it is accelerating as it's going. So you'll assume here that you are maintaining some constant force, so that you maintain constant tangential acceleration all the way. All right. So in this case, here there's going to be the normal force due to the surface. There's going to be mg. Here there's going to be mg this way. And then there's going to be the normal force that way. Even here there's going to be the normal force. And then there's going to be mg. And then here there's going to be mg. And then here there's going to be the normal force. So you could come up with certain equations. If you look at the forces in the y here, it's just going to be equals to Fn plus mg is going to be equals to, remember your Fr here is also facing in that direction, is going to be equals to Fr. And basically this is going to be Fn plus mg. So how I got this is minus Fn minus mg, and Fr is also pointing down as minus. So all these minuses, they become pluses because I divide by minus afterwards, which is mv. Now v what is 0 squared over r. What about here? Here, the only force that is contributing to the centripetal force is just going to be equals to, the only force that is contributing to the centripetal force is just Fn, which is going to be equals to the centripetal force, which is mv1 squared over r. That's the only force. If you look at mg, this force here, mg, is just going to be equals to the mass multiplied by the tangential. Is going to be the mass multiplied by the tangential acceleration. So in a way, you could say that maybe here you're applying a force and then you leave it because the weight is doing now the force, the weight is doing the work now in order to maintain the constant tangential acceleration. So basically here, all the tangential acceleration is due to the weight. Basically, that's what it means. If you look at here, for instance, here you have to probably when it comes here, for instance, generally it has enough energy to come here, all right, to get here. It also depends if they say the friction is if they say the surface is friction, then that is a little bit of hell. All right, so let's just assume that there's no friction, otherwise it's just going to be a mess. All right, so here what you have is you have Fn minus mg is just going to be equals to Fr. So basically here is just Fn minus mg is going to be m v what? v2 r squared, right? v2 squared divided by r. So that's one equation, all right, that you can have here. So you could be applying a force on your engine, and then that force is the one that is giving you the tangential. Whatever force that you're applying on the engine is the force that is actually making sure that you maintain some tangential acceleration. So you could have something like that. But if you're just considering what is happening in terms of the centripetal forces, you are having a situation like this. Even here, for instance, you could be having a situation. You can be having a situation like Fn is just going to be m v3 squared divided by r. Okay, in terms of the centripetal acceleration here, because there's mg, you want to go up, mg is going down, so you will need to apply a force. For instance, if you want to maintain acceleration here, what is going to happen is that you must have a situation whereby you apply a force upwards, then there's going to be weight, then that is actually going to be equals to mat. That is the way that you can actually get the centripetal force. So your engine has to do more work here when you're going up because the weight is actually pulling down. Okay, all right, so you'll have to apply forces. Even here we probably have to apply forces. Here as well, it just depends. So you may have to apply forces in certain areas, you may have to not apply forces in certain areas, or apply force in a different direction. For instance, if it's too fast, if you want to maintain the same tangential acceleration, you may have to sort of apply a brake a bit so that you maintain whatever the acceleration that you want to accelerate. It depends if you want to maintain a constant centripetal acceleration. Now, because there's so many things that are at play here, so it's not like it's moving. If you wanted to maintain a constant acceleration in a flat surface, you just basically apply the accelerator, keep it constant. That's it. But here, because the FR is changing. So you always have to adjust to a number of things in order to ensure that your acceleration is actually constant. All right. Generally, to be honest with you guys, you hardly get to consider these situations here, whereby they're asking you what's going to happen with the tangential acceleration. You hardly get it. So I wouldn't really concern myself too much with this. All right. So I think this is good. And then maybe just one case that I may want to do, which is a little bit complex, is maybe let's just do a case whereby maybe my card is somewhere here. All right, so what will happen if my card is somewhere here? Now this one is a little bit complex, but then I can just set it up for you guys to just have an understanding as to what is happening. All right, so in that case, for instance, if you're having a car and the car is somewhere, there's your setting, and you want to find out what's going to be when your car is somewhere here, what's going to be what is the setup. So remember, now your FR is in this direction and your FT is in that direction. So if we draw it, this is FT and then this is FR. But now another thing that we have to now look at it in terms of the weight is always going like this is mg, and then but then your normal force now is going to be facing that way in the direction of fr. Okay, so your normal force, so you have to have a Cartesian plane like this, and then if you have a Cartesian plane like this, you could choose a Cartesian plane like this if you want. You could choose something like that if you want, but I'm just going to choose a Cartesian plane like this just to show you how the angles are going to fare. Right, so if I choose a Cartesian plane like this, look at my ft is like this, and then makes 90 degrees with fr. Now I'm saying I'm choosing a Cartesian plane like that. Let me use a different color. There it is. I'm using a Cartesian plane. So if I extend this Cartesian plane, there it is. So what do you notice? You notice that now if this is theta 1, these thetas may not be equal. Right, this is theta 2. You will see that now my f my fr has an x component, and then it has a y component as well. All right, that's basically my fr. So it has a y component, it has an x component. This is frx, this is fry. Even this one, the tangential component, has the x component. This is ftx, and then it has the y component, which is fty. So if you were to set up all the forces in the x, even if I have the Cartesian plane here, if you look at this is already in the y. This is, so you can see that my is going to be theta 1, this one. So even this one is going to have the x component. There's the x component f and x, the y component f and y. All right, so now you could set up what are the forces in the x, what are the forces on the y. I know it's now a little bit complex, so we have to look into that. So if you look at all the forces that are in the x, you just have this fn x. All right, and that's the only force, generally that's the only component that is in the x direction, and that is just going to be equals to m ar, because basically, okay, let me just break it down so that you understand. All right, so you're saying this is going to be equals to ma, but remember the vector a is ar plus at. It's always true, it's just that when they are here, you'll find that at is 0. Maybe, like for instance here, 80, if you're looking at the x direction, 80 is 0. If you're looking at the y, ar is 0. So it's always true, it's just that at some points they are 0, the other component is 0. That's why we didn't consider it. So this one basically becomes fn. Then you could say this is going to be cos theta 1 is going to be the mass. What is going to be a? And then this is going to be ar plus at. All right, this is the same as m ar plus m 80. All right, now these are vectors. Let's just have everything as vectors for now. And then this is minus fn. The right hand side I've already considered the direction. Now if you continue with this and then you just do it further, so you can see which sides are negative, which sides are positive. Then what happens is that if you look at mr is going to be negative, because it's in the negative direction. But then if you look at the x component of t, the acceleration is going to be positive there. So basically we're just going to have something like this, and then this is going to be the mass. So fr is negative, so since it's negative, the x component is negative, so it's going to be negative m v squared, whatever the velocity is there, over r. And then this one is just positive, and then it's just going to be empty. Remember, at is just the change in velocity over the change in time. That's basically where you're going to get the magnitude of at from. You could also set up the forces in the y. So here the only force that was in the x was just that one, but here the forces that are in the y, you have minus fny, you have minus mg, and that is going to be equals to, everything is minus and minus, you have minus fry. But basically what you could say is, you could say like that, you could say this is going to be m, and then you have two components, so you have the y for the fr, you have the y for the ft. So in that case, because of that, you are going to have AR in the Y. Sorry, I forgot to put the X here. We are just considering the X-axis here. Everything is in the X-axis, all right? And if you are considering in the X-axis, I have to sort of correct this equation, sorry. Okay, so if I correct this, this is going to be M. The magnitude of AR, I mean, this is basically AR, and then this is going to be cos of theta 1, and then it's going to be negative, and then this one is going to be m 80 cos of theta 2. All right, so it's fine. I mean, you can just substitute AR. And then here it's just going to be ARY is still a vector, plus ATY, which is still a vector. So if you break it down, this becomes Fn, and then this is going to be sine because it's opposite that. So it's going to be sine theta 1. So I'm hoping that you, I mean, I'm taking, you have done vectors, you have went through the video where I showed you guys how to work with vectors, you have went through the video where I showed you how to work with forces. So we are building up on this, hence I'm a little bit faster when I'm teaching this section, because I'm expecting that you should have gone through that and you know how to actually, or you should have some knowledge on how to actually break these things into components. And then this basically becomes mg, and then this basically becomes m, and then let's just open space. This becomes m and multiply with this ary, but ary is the same as ar sine of theta 1. Is it positive or negative? It is negative, so I'm going to have negative here. There's my equal sign, there's negative. This one is going to be negative or positive, is negative, so it's going to be negative m, right, which is this m, and then you multiply it by aty, but aty is 80, whatever the value of 80 is, sine of theta 2, all right? So of course this is the same as just fn sine of theta 1 plus mg, because everything is facing down, so it's cancelling out. Ar sine of theta 1 plus 80 sine of theta 2. All right, so basically this is how you could actually just work it out. I mean, if you wanted to work out something that is somewhere here, I'm just doing this in case, you know, I don't know, maybe you get a lecturer that really likes challenging you guys. I mean, there's so many things that we can do here. I mean, we could give you the car and then say there's friction, and then it's just basically we have created a little hell there that you'll be having when you're writing it as a test or as an exam. It's just not going to be very friendly working it out. but you could have a situation like that. All right. Okay, so let's just move to another one. This section that we are going to move to is basically what happens when your cars are actually turning a curve. All right. So for instance, you have a curve. I'm not going to draw very well. There's my car. There's my car. Believe it or not, it's a car. And it's basically turning a curve. There's your curve. So the question is, what happens? All right, as it's turning a curve like that. So what happens is generally the tangential velocity, this is what the tangential velocity is. Now, if your car could not turn this curve, generally to roll out in this direction. So generally you need friction to keep it moving in that direction. So you need some frictional force. Now this frictional force is normally static friction on your car tires, and it's normally acting inwards like this. It's the one that actually ensures that your car doesn't go out of the road of your road, and then it doesn't roll that way if it's rolling. All right. If it's skidding, meaning that it's just sliding, it's going to start sliding in this direction. All right. So when it slides, it's going to slide in that direction. If it rolls, it's going to roll in that direction. So the static friction is keeping it from sliding and from rolling, basically. So it's making sure that it can actually turn your curve, right? Without sliding, without anything, right? So this is just a flat surface, so nothing else here. So in this case, the only thing that you could do is you could say, well, the sum of the forces here is just going to be equals to Fr, because that's basically what is going to happen. I mean, you could extend this. This could look like a circle like this, right? So this curve could look like a circle. I know it's not complete, and then with radius r, for instance. So in that case, for instance, you just have that. And then what is the force there? Static friction is the only force. There's static friction. And then this is going to be equals to mv squared. Let's assume that it's moving at a constant speed, mv squared r. Okay, this is of course it's just given by ms and then fn. And then this is going to be mv squared over r. All right, this could be like fs mg mv squared over r. Then the m's are going to cancel one another. So you could find the speed if you want. I mean, if you want the speed, it just depends on whatever it is that you want. It just depends on what you want. All right. So I mean, this one you could like it's mu s g equals to v squared over r. So how I found that it's I mean, if you look at the sort of the view, the back view, as your car, if someone was looking at your car from the back side, it would look like that. And then these are tires, right? So there's going to be, and then this is your window. These are your lights. Okay, this is your number plate here, right? So if you look at it like that, this is going to be FR. Of course, this is going to be FN because there's a surface here. And then there's going to be MG here. These are the forces that are acting on your car, basically. All right, and then that's why I couldn't really get that equation. So I'm teaching a little bit faster now because I'm expecting that if you're already here, you're already doing this section, means you have learned quite a number of things. You have learned forces, you have learned quite a number of things, and it's a little bit more easier for you to now actually analyze this. All right. Okay. All right. So if, for instance, you were given that r is equals to 30 meters, and then you were told that the car is actually moving at 20 meters per second, and then you were asked to find this coefficient of static friction, you just say the coefficient of static friction is going to be equals to v squared over r multiplied divided by g, like that. All right. Then you could just find it, and then which is going to be 20 squared, and then g is 9.8, and then r is 30, and then the coefficient of static friction needed for you to have in order for you to turn that curve at that speed is actually going to be, all right, so it's going to be 1.4 basically, which is high, right? It's a bit high. All right, so that's your static friction that you're going to need in order for you to sorry, in order for you to be able to turn that curve. All right, so they would design, normally what they would do is they would design roads in such a way that it allows the car to have a maximum speed. So they'll say that is how they determine that when you're turning curves, and then they say your maximum speed is travel at 80, travel at 60, because certain curves are designed to travel at a certain maximum speed. So they've calculated the static coefficient of friction, the coefficient of static friction. They've calculated the angles. I'm going to get into that, or whether it's flat or it has an angle, and then basically they take all of that into account. All right, that's how basically the engineers know. All right, so the problem that I just did, whereby it's just a flat surface, is normally known as unbanked curve. But normally what they do is you could design your curve such that it's banked. So when it's banked, it's like this, it's at a particular angle theta. Okay, so your car is going to be like that, basically. That's basically how your car is going to be. All right, there's your car, these are your tires. So you're expecting your car to be like that, and then of course your car is going that way, forward that way, V is going that way. So this is your curve, basically. There's your curve. So your car is going to turn this curve. All right, so you could extend it like that. I'm just drawing it so that you can see how it is. All right, so you know cases like this whereby your car is sort of at an angle and then it's tilting, and then you have that situation. All right, so of course here, let me just, I can remove this because I want to draw the forces. Oh, it's fine. Okay, so you could draw a circle here. Maybe there's a circle that, so it's not, the whole road is not going to be a circle. Maybe the circular path is just going to be this, and then this is R basically. All right, so if you look into this, there you have your car like that. I'm just going to draw it as a block, and then it's going to have Fn like that. It's going to have Fg like that. All right, so you want some static friction that is going to be, because your Fr is going to be here. Fr is going to be here. The circle is here, so your Fr is going to point that way. So you actually want what force is going to actually provide this Fr. So if you look into this, you can actually see I could draw this Fn. So let me just remove this Fn here. You can actually see that I could actually draw this Fn to be like that, and then this is F perpendicular is perpendicular to that, and then you could have it like that, and then this is F is a perpendicular. Okay, let's just say Fy, and then let's just say Fn, and then there's your theta here, and then there's your N. So the normal force actually provide this Fx, which is going to be in the direction of Fr, such that if I sum all the forces in the X, they are going to be mv squared over R. Okay, so meaning that this Fx here is going to be mv squared over R, which is going to be Fn, and then sine of theta is going to be mv squared over R. Okay, so this is me assuming that there is no friction here. I don't need friction, so because this Fx serves the same purpose as the friction would serve in this case. All right, then the other one, basically, if I sum all the forces in the y, there isn't any going up or down, so it's going to be equals to 0. So let me just write it somewhere here. So the sum of all the forces in the y, they are going to be 0. What are the forces in the y? It is Fy minus mg is 0, which means that mg, no, not mg, which means that Fn cos of theta is going to be equals to mg. I just took this mg, put it this side. That is going to be that. And then from here, what you're going to have is you basically have this as equation 1. You basically have this as equation 2. So what you could do is you could take equation 1 and divide it with equation 2. When you do that, you end up with Fn sine of theta is going to be equals to mv r squared divide both sides with whatever is in equation 1 is Fn cos of theta, and then here you're dividing with mg basically. So this and this cancels, this and this cancels, and then you end up with sine over cos is tan of theta. Tan of theta is going to be equals to v squared over r divided by g, so this is gr like that. Okay, so if you wanted to find out what is going to be the speed that is going to be required, it's just basically going to be gr tan of theta, and then you put everything under the square root. That's what's going to be the speed. All right, so you could easily calculate again. I could just put in the values and say this is the radius and this is theta. Find out the speed that you need in order for you to turn the banked curve. So an example would be is again, if you do want me to go through examples, I could. The important thing here is just to learn how to go through everything. Okay, derive everything. All right. Now the question is, what happens if a car is turning a banked curve? So remember I said there's no friction there, I don't need friction, but now there's friction. Now this is normally the case whereby you do need some friction because, for instance, when it's rainy, your car will not be the normal force, the component of the normal force is not enough to actually keep the car moving in a circular path at a particular speed, depending on whatever speed that you're moving with. So in this case, you do actually need the friction to be actually present there. Right, so now we have to consider the case with friction and then see how actually it's going to work with friction. Right, so it's a similar case whereby I have this, there's my banked curve, so everything is fine, there's theta, and then there's my tires, and then I have that. All right, then let's look at the forces. Of course, remember my circular path, the circle, the mini circle is actually horizontal like this, so you need that force because there's my r, small letter r, so you need that force that is going to be in that way. You need Fr in order to keep this moving in circular motion. All right, you need it in circular motion. In order for you to move it in circular motion, you need that Fr. Okay, so what would be that? How do you consider it? Now let's look at the forces. So I'm just going to draw it as an object like this. There's going to be a normal force, we all know that. Okay, that's fine. There's going to be the weight. Maybe let me draw it. I don't know which side do I draw it. Fine. Okay, let me write it this way. I'll see. Now, remember, because there is the component that is actually going this way, so now you have to have the friction that is actually going to go that way. So your friction will be going that way. Okay, so that your car is not slipping, it doesn't skid and all of that. Okay, so your friction has to change. All right, so you do need some friction that is going to go that way so that it prevents your car from basically going that way, right? Because remember the road is now slippery, and now when it's slippery, two things can happen. You can have a situation whereby your car is going to start skidding basically, or your car is actually going to start going that way, and also depending on how fast you're moving, you can actually roll out as well. So there's just so many things that can happen because the road is wet. All right, so you can see now what I'm going to do is I'm going to choose my x to be like this in this case, then I'm going to choose my y to be like that, because if I don't do that, things are going to be very complicated. So I am going to choose my x to be in this direction. I'm going to choose my y to be in this direction. Now remember, my acceleration vector must be in this direction because my circle is basically horizontal like that. So my acceleration vector must be in that direction. That's the direction that I want my acceleration vector. All right, so if you look into this, you can actually see that basically what you have for this acceleration vector, you are going to have a component of the acceleration vector that is going to be parallel, I think. Yeah, just parallel, and then you are going to have a component that is going to be perpendicular in order for you to actually keep your AR to be like that. because you want AR going inside like that, but your car is tilted. Okay, so look at the sketch on the left, and that's how basically I'm determining everything. Okay, all right, and then basically now you can break it down like this. So if I break it down, I'm going to skip some steps maybe, and then let me just say the sum of all the forces in the X, they are going to be equals to M, right? A Rx, which is R, which is AR parallel, which is this parallel, AR parallel, all right, in the X. If I sum the forces in the X, that's what I have. So what are these forces in the X? Remember, I have this F. I have this F perpendicular, and then I have this F parallel. Now I have the F parallels here, unlike the first one. All right, so here on the X I have this F parallel, and then I have this minus Fs, and then I basically have this MA, and then what is that? A, that's MA parallel. Okay, so I mean you could substitute this is the same as mg. I think if I put theta here, and then it's parallel, right? So it's going to be sine, this is going to be sine theta, and then this is just going to whatever Fs is. Maybe if you're looking for a static coefficient of static friction, then this is going to be Fn, and then this is going to be M A parallel. Let me write it like this. This becomes mg sine of theta minus Fs like this, and then this is Fn. This is equals to, what is MA? This is A, and then AR, whatever AR is, and then you say this is going to be cos, because you're going to have theta here. So this is going to be cos of theta. Okay, so the sum of the forces in the Y is going to be equals to MA perpendicular. Okay, so this is going to be Fn minus F perpendicular, and then this is basically going to be MA perpendicular. This has to be plus, sorry, it has to go up here, right? You have your AR vector like this, and then this is your A parallel, and then this is your A perpendicular. It has to go up like that. All right, so I'm going to write this down. Fn is Fn. I don't know what Fn is. This one is going to be mg cos of theta, and then this one is going to be M, and then this is AR, and then AR is going to be sine of theta. Now remember that AR, you could substitute, I mean you could say this is Fn minus mg cos of theta is equals to M, and then you say V squared over R sine of theta. You could do that. Even here you could say it's mg sine of theta minus that Fn is equals to MAR cos of theta. All right, so you could just have this as equation 1, you could have this as equation 2, and then you basically solve whatever it is that you want to solve. So I'm not going to give you a problem, so I'm just breaking it down for you so that you have an idea as to how you could approach the problem, and how you could actually solve it. If you really want me to do problems on this, I know that this chapter is a little bit difficult now. This is more now when you're getting to university level now. Then most of the time, here in South Africa especially, the curriculum is designed such that they don't do this at high school. This is now this is what is actually done at university. So it gets a little bit complex, a little bit complicated, and also with the upcoming chapters like your rotations, oscillations, and everything else. So things can get complicated from here onwards. All right. I think though it's fine. Let me stop here. I'll just wait for your comments. And here, if you guys really want me to maybe break down things, maybe in a simpler fashion, do examples, and then I'll come back and then just have a look at that. All right. Otherwise, guys, I think that is fine. I'm happy with what we have done so far, and I'll see you guys in the next video. Cheers.